6.2. Today we're going to talk about the natural base e. First thing I'd just like to say, if anytime through this video, if you are confused or you're not understanding something, don't be afraid to stop the video and rewind it and maybe watch a portion of it again. If you are still not grasping something, maybe you could ask a classmate and see if they could explain it to you. And then if you have any questions over this, make sure you see me Monday, either before school or SRB. Today we're going to define and use this natural base e. We're going to talk about what it is, how we calculate it, and then some things about it. We're going to graph these natural base functions, and then we're going to solve some real life problems. All right, now you're going to need a calculator, so if you don't have one, pause the video now and go grab one. Now we're going to start with a little situation here, situation, and it says that Mr. Cole is in need of $1. Okay, and you are graciously going to lend him this $1, but you're going to charge him 100% interest per year. All right, and obviously you want to make some money off of me, so you are wanting the most money possible, so you are debating how often the interest should be compounded. Okay, so last class we talked about compound interest, and our formula for compound interest was A equals our principal times 1 plus our rate divided by the number of times it'll compound times to the nt power. Okay, that's our formula that we used last class. Now, we're going to use this formula to help us fill out this chart. All right, now if I look here, I want to know how much you're going to make if we compound once a year. So if I look at this, I've already put in 1 for the rate. Well, you're going to charge me 100% interest. So 100% written as a decimal is 1. So I already put a 1 in there all the way through. And if the number of times we're going to compound here is going to be 1. And I need to raise it to the nt power. Now n is the number of times we're going to compound, and t is time. Now for this situation, let's just pretend we're only worried about a year. Okay, so after 1 year is up, I'm going to pay you back the money that I owe you. Okay, and so the number of times we're going to compound is 1 times the year, which is 1, so this just becomes 1. Okay, so I am going to have you guys do some calculations for me, and I will do them also right now. So if we're going to calculate this, I'm going to take 1 divided by 1, and 1 divided by 1 is 1. I'm going to add 1 to it to get 2. I'm going to take 2 to the first power, which is 2, and then times my principal, which is $1, and this gets me $2. Okay, that means that if you compound 1 time at the end of the year, I will owe you back $2. So you're going to get the $1 back that you lent me, plus you're going to make $1. Okay, not too bad for only giving me $1. Now, let's say we want to compound twice a year. So we need to take it to the second power again. So in your calculator with me, take 1 divided by 2. That should get you 0.5. Then add 1 to it. That should get you 1.5. Then square 1.5. And then times that number times 1, which we really don't ever have to do because timesing by 1 doesn't change the number. And I believe you get 2.25. So if you compound in the middle of the year and at the end of the year, you will gain an extra quarter. Okay, so I'm going to have to pay you back the $1 plus an additional $1.25. Now let's think about quarterly. Okay, so if you compound quarterly, I need to take 1 divided by 4, which is 0.25, add 1, which is 1.25, and then take that to the 4th power. And when I take that to the 4th power and I can times my 1, I'm going to get 2.441. Okay, so about $2.44. So you're thinking, golly, if I compound quarterly 4 times a year, I'm going to make an extra 44 cents. All right, now let's try 6 times a year, which is every 2 months. Okay, so the calculations will start getting a little bit more complex, but I'm going to take 1 divided by 6 on my calculator, add 1 to that, then take it to the 6th power, and I think you should get 2 2.522. So now you're over $2.52. All right, we're gonna keep going here. Now, actually, I'll stop. What do we notice between $2.25 and then $2.41? Well, I think this is a change of 25 cents, so about a quarter. This is a change of what? I think that's like just 19 cents. This is a change of, let's see here, 6 to 50. Is that about 8 cents? It's only about 8 cents. So the amount that we're increasing is going down, but we're still increasing. All right, so if I go over here and let's talk about 12 times. So let's think about monthly. If we compound this interest monthly, and we'll in our calculator take 1 divided by 12 and hit enter. Add 1 to that, hit enter. Take it to the 12th power, and I think we should get 2.613. So again, we're still increasing, but I think I only went up, yeah, I didn't go up very much there. Okay, I doubled the amount that I compounded, but I didn't go up very much. All right, now let's try 100. Well, we're kind of getting crazy, and let's say, hey, let's compound 100 times a year. So 1 divided by 100 plus 1 raised to the 100th power, and we should get 2.705. All right, still increasing, but not by near as much. And let's think, you know what? Let's do 1,000. Let's compound 1,000 times. So 1 divided by 1,000, hit enter, add 1 to that, and then take it to the 1,000th power, and we should get 2.717. So if I compound, the difference here, guys, between compounding 100 times and compounding 1,000 times, the difference there is really just a penny. Just a penny. Now, let's do 100,000 just to see what this is. So we're going to plug in 100,000 here. So 1 divided by 100,000, hit enter, add 1 to it, hit enter, and then take it to the 100,000th power, and we should get 2.718. So I increase the times that I've compounded by 99,000 times. So I've compounded 990,000 times more, and I only went up 1/10 of a penny. Okay, so as you can see, the more times I compound, the more I'm approaching this number. Okay, I'm not increasing by near as much anymore. Okay, so to answer this question, what happens as the number of times it is compounded increases? Well, we've talked about that. It's going to increase, but the amount that it increases is decreasing. Okay, so it's going to kind of level out. Now, what is the maximum amount of money you will get from Mr. Cole? Well, it looks to be about $2.71. Now, if you want to round it, you could call that 72 cents, maybe, but that's not cents, not percent, but cents. So $2.71 or 72 cents. Okay. Now, this number is called E. All right. So everyone in your calculator, I want you to look at the division button. On the division button right above it, there's a blue E. So if you hit the second button and hit the divide sign and hit enter, that number is E. E is about 2.718281828. Okay, this number goes on and on and on forever. Okay, and it is calculated by doing exactly what we just did. Okay, so that, to be exact, is the most money you could make from me in this situation. Okay, now we're going to talk about compounded interest in a little bit, but let's scroll down here. to example 1. Now, e is, again, just this number. It's an irrational number that keeps going on and on forever. Now, one thing we need to understand is we can treat e kind of like a variable. And we're going to do very similar things to e that we would to x. So if I look at example 1 here, e to the third times e to the sixth, well, I'm going to add my exponents here and say that's e to the ninth. Now, I can evaluate that because e really is a number. Okay, we're going to keep it as e to the ninth because it's the most accurate way of writing the answer, but if needed, I could evaluate that in my calculator. Okay, if I go over this second example, I have 16e to the fifth divided by 4e to the fourth. Now, 16 and 4 are coefficients, and I can simplify those. So 16 divided by 4, well, that's just going to give me 4. Okay, and here I have e to the fifth divided by e to the fourth. Well, I can cancel 4 of those and cancel 4 of those, so I'm just left with e. So the answer here would be 4e. Okay, this one's a little bit different. I'm squaring both of these things, okay, the 3 and this whole e to the negative 4x. So I need to distribute my 2 essentially to both. And 3 squared is going to give me 9. And then when I do this, okay, if I had 3x squared, and that's squared, well, I'd have to multiply my exponents. So I have to multiply this. I'd get e to the negative 8x. Now, we don't like negative exponents. So I'm going to cut, edit, paste this guy onto the bottom. So I'm going to move it to the bottom. I'm going to keep 9 where it is. There's nothing wrong with 9. So I'm going to have 9 in my numerator. And then in my denominator, I'm going to have e to the 8x. And 8 becomes positive because now it's in the denominator. Okay? All right, we're going to come back to the compound interest here in a second. Now, we're going to talk about natural base functions. A function of the form y equals a times e to the rx is called a natural base exponential running out of room here function. Okay, it is essentially just going to be an exponential growth or decay function, but we're going to use e, okay, as our growth or decay factor. Now, when a, this number in front, is greater than 0, and r is greater than 0, that number right there, the function is an exponential growth function. Okay, when a is greater than 0 and r is less than 0, so r is negative. So when we have a negative exponent, the function is an exponential decay function. So in my two pictures here, I am graphing e to the x. Okay, e to the x. And just like we did last class, I know when it's just e to the x and not a times e to the x, but rather when it's just e to the x, the graph will always go through 0, 1, and then 1, e. Okay, in this case, e, so it's going to go through those 2 points. Exponential growth. Okay, exponential decay, so here I have y equals e to the negative x. Okay, and since we've got a negative exponent, it's going to be an exponential decay. Okay, so if I go to example 1, okay, we're going to use our graphing calculator here. So why don't you right now type in to y equals, I'll do it as well, 3e, and again, e is second divide sign, and we're going to raise that thing to the x power. can hit graph, make sure our window is set normal, so we could hit zoom 6 if our window's weird. And we see that. Now let's go to our table, go second table, and let's plug some values here. Now, since I have this number here, when I have 0, well, 0, e to the 0 power, anything to the 0 power is 1, and then 1 times 3 is 3. So at 0, I'm going to be at 3, and we see that on our x and y table. All right, now at 1, I am at 8.15. So I'm up here at 2, 4, 6, 8.15 right there. Okay, at negative 1, I'm at 1.10. Oh, of course that went away. So I'm going to be at 1.10, just above 1. At negative 2, I'm at 0.406. Okay, and as you go down our x and y table on our calculator, actually go up, you can see if I go take my x all the way to negative, let's take it to negative 10, and actually let's go negative 7, negative 8. And if you guys look at that on our table, we're getting really small over here, very close to 0. But if you look, it eventually gets to e, this e thing, which that is scientific notation. We're never ever going to get to negatives. It's always, that number always stays positive. And the reason for that is because we have a horizontal asymptote there, just like we did from Wednesday. Okay? Now, is this an exponential growth or decay? Well, this would be growth. Why is it growth? Because our exponent is positive. All right? Now, this is going to be a decay because our exponent is negative. Now, let's type that into our y equals, please. And graph it, and we can see that it's going to be a decay. And if I go to my x and y table, let's plot some points here. 0, and when I look at 0, of course that's going to be 1 because I don't have an a value in front here. So anything to the 0 power is always 1. If I look at 1, it's 0.606. If I look at 2, it's 0.367. So 0, 1, 1.6 and 2.3, so we're decreasing there. If I look at negative 1, I'm at 1.648. So right there, and if I look at negative 2, excuse me, it's going to be 2.7, and if I keep going, it's just going to keep increasing. So now this is an exponential decay model. And again, we're going to have a horizontal asymptote at 0. Okay, so when graphing these today, use our graphing calculator. They're not as nice and even because e is an irrational number, but we can certainly graph these on our calculator. Now let's go back to the front of our notes, and let's talk about this idea of compound interest, but it's continually compounded. Okay? So what this means is we're going to compound constantly. All right? So we are going to compound not every day, okay, more than every day, basically every second of every day. It's just always going to be compounded. And our formula for that is A equals P e to the RT. Okay, where our A stands for our account, or our account balance. P stands for our principal. R is our rate. It's important that we have our rate to be a decimal. And T is our time. in years. Okay, so if we are going to be compounded continually, we're going to use that formula. So let's go to the bottom of our backside of our notes here. And it says, you and your friend each have accounts that earn annual interest compounded continually. Okay? The balance, A, in dollars of your account after T years can be modeled by this function. The graph shows the balance of your friend's account over time. So there's our friends. This represents us. All right. Which account has a greater principal? Now, principal, that was bad. Principal is our starting value. So if I have this function, A equals 4,500 e to the 0.04t, okay? If I have this number represents my principal. So I started with 4,500, and if I go to my friend's account, well, I can figure out how much he started with by looking at the year. And we want to know, starting, he was at year 0, and at year 0, he was at 4,000. So which account has a greater principal, starting value? Your account does. Your account and that starting value is 4,500. All right, the next question says, which has a greater balance after 10 years? Okay, so if I look here at my friend's graph and go to 10 and go up and figure out where the graph is, that looks to be, let's see here, just over $7,000. Somewhere between 7 and 8, closer to 7. So your friend has just about $7,000. Now, why don't we type our account, our equation into our y equals. So 4,500, and then we're going to do E, and we're going to raise that to 0.04x. And we can go second table. And I want to go to 10. As you can see, if you type that in and go to our table at 0, we have $4,500 like we're supposed to. And if I go to year 10, it looks like I have $6,713.20 in your account. Well, if I look at your friend, it appears that he has over $7,000. So to answer the second part of the question is, which has a greater balance after 10 years? Well, it would be your friend, and it's going to be just over $7,000. Okay. Again, if you have questions or concerns over this, you can try watching the video again, talking to a classmate about something, or please see me in SRB on Monday. Your assignment is going to be online. Please be showing your work whenever possible, and have a great weekend.